So we'll pick up our discussion on where we left off last time. We said that we could read and write to memory, right? We figured out how to create memory and how we can read and write from memory. This is a schematic for a processor. So let me basically go over first how the processor works. You have a program that runs and you have instructions, and those instructions are stored in this area right here. This is called the control store. So your program, which is a series of instructions that map one-to-one to the architecture of this machine, are in this area. Your instructions get read into what we're going to call an instruction register. So your instructions are, in the end, going to be a bunch of zeros and ones. Those zeros and ones will either turn electrical wires on or not on, and depending on what wires are on or not on, will determine what operation is going to happen. Okay, so the architecture here basically has, we talked about last class, we talked about how we had one nibble of memory that we can write to and read from. In this case, we're going to have 16 32-bit registers to read and write from. So this architecture has a 16 register scratch pad area where we can, so for example, we can put an address on the MAR. So the MAR is a big decoder. We put an address, so memory is, let's say, out here. We put the address that we want data from. The address we put on here will allow data to flow into our NBR, which is our memory buffer register. That's where the results get written to. And then we can take that result and put it into one of our registers for a later computation. Okay, now, our computer, this is the symbol that means the ALU. So it always has two inputs coming into the top and one output coming out of the bottom. And our ALU can perform 4 basic mathematical operations. So in our instruction, we have 2 bits dedicated. I'll blow this up in a second and go over what the bits mean. But we have 2 bits dedicated for which ALU operation we can do. And on this architecture, we can do, if the bits, well, I'll get to the chart in a second, but we can add 2 numbers together, the 2 numbers that come in, we can add them together and have the results come out. One thing we could do is we could take one of the input numbers, the 2 input numbers, and we can AND the bits together. I'm not really sure what the mathematical value of doing that is. Another thing we could do is we could take one of the input numbers and have it go through the ALU untouched. And the reason we're going to do that is sometimes we're going to want to just look at a number and maybe set some bits based on that number. We don't want to perform a computation on the number. And another operation we can do is we can take one of the inputs and we can take the complement of it. Every bit that it has, we can flip the bit over. So that's a really easy piece of mathematics we can do, because all you do is take all the bits that came in and run them through an inverter, a NOT gate, and then take the results, right? And if you remember when we talked about recording numbers in memory, if you take every bit and flip them over, you've recorded the negative of the number. So you could take the number 5, 0, 1, 0, 1, flip all the bits over, and now you have negative 5. So the 4 operations we can do is we can add 2 numbers together, we can take a number and calculate its negative, we can perform a non-operation, and we could also take 2 sets of numbers and AND the bits together. Okay. This is a piece of equipment called a shifter. Again, a very simple piece of mathematical equipment to build. All you're doing is taking a bunch of bits and shifting them over one unit. So if you take a binary number and put a 0 in front of it, you double the number. You know, just like in Just like in decimal, if you want to multiply a number by 10, the base, you put a 0 on the rightmost side, and you've multiplied it by 10. So in binary, if you put a 0 on the rightmost side, you've doubled the number. If you slide the numbers over 1, you've divided it in half. So we can do some very basic multiplication and division using shifting, taking a bunch of numbers and shifting them over one bit. Okay. When your program runs, we're going to take an instruction from our program, load it into our instruction register, have all the wires, all the electricity flow to our processor. The very next instruction we're going to do is we're going to take the program counter, that's a register that points at your current instruction. We're going to run it through an incrementer. Yet another piece of very easy mathematics to build. You just take a value and you add 1 to it, and then take that result. So the very next instruction, when you say, you know, A equals 10, B equals 15, your program runs an instruction, the very next line is the one right after it, and so on. If we had an if statement in our program, if the clause we tested turned out to be false, then the next line is not the line right after it. The next line is somewhere else in the program. So we have to have a mechanism for that. So every instruction we do, we're going to run it through this incrementer to get the next value. But every once in a while, depending on the result of an instruction, we may jump somewhere else. Also, if you had like a for loop or a while loop, at the end of the loop, when you get to the bottom, you would want to jump back up to the top of the loop. So not always do we go, is our next instruction the one right after the current one. Sometimes it's a totally different location. Okay, so now let's take a closer look at the instructions itself. So here's our instruction. We have a bit, we're going to call the A, the first, mux. So mux is a multiplier. So what this is going to do is say, our 2 inputs to the ALU, the 2 things that we may accept as input to perform a computation. One of the inputs has 2 choices where it gets its data from. Should it get it from one of our 16 registers, or should it get its data from our main memory? We have a choice. So you can kind of think of it like we have 3 inputs to the ALU, but one we have to pre-pick. Which one do you want? So if this AMUX bit is turned on, if the AMUX bit is on, I'm sorry, if it's off, if it's 0, then we get our input from one of our 16 registers. And if it is on, we get our input from memory. So if this bit is set on, then this value is fed into the left side of the ALU, and one of our registers could fit in the right side if we're doing a 2-operand operation. So we determine where we want the input coming from by setting this bit on or off. Okay. So now, the condition, there's 2 bits for conditions, and I'll go over an example a little bit later on that makes use of this. But what the condition is basically, there's 4 different things we could do. We could do a no jump, which means the very next instruction we run is the instruction right after the current instruction. We could say, based on the most recent operation of the ALU, if the result was negative, so the N bit will be turned on, if the result of the previous operation was negative, we could jump if the result was negative. If the condition code is set to 2, if the condition code is set to 2, if the condition code is set to 2, and the Z bit, this is the N bit coming out in the Z bit, if the result of the last thing that went through the ALU, if the result was 0, the Z bit would be on. And if that bit is on, then we would take from this mux we would take the address in our instruction as our next instruction, not the instruction right after the current instruction, but we would jump to somewhere else, whatever address we put in here. So that'll be a little bit more clear when I go over an example. Okay, our ALU can do one of 4 operations. It can take the first input and the second input, and it can add them together. It can take the first input and the second input and take all the bits and AND them together. It can take the input from side A and let it pass through undisturbed, which we're going to do to kind of set those 0 and end bits later. And it can take the complement of what comes in on the A side. And the complement of a number is really the negative of itself. Okay. We have the option to do this kind of very primitive multiplying and dividing by using the shifter. If the shifter value, if these 2 bits are set to 0, 0, we don't shift. We just let the data flow right through. If it's set to 0, 1, we shift to the right. If it's set to 1, 0, we shift to the left. And if it's set to 3 will never be used. So we can either let the data flow through, let the data that comes out of the ALU, just let it flow straight through untouched. We can shift it to the left, we can shift it to the right. So that would be multiplying it by 2 and dividing it by 2, if we wanted. Okay. By turning the MBR and the MAR on, we are allowing data to flow into them. By turning the read flag on or the write flag on, it's telling us whether we are reading from memory or writing from memory. So the read and the write flags would be kind of like what we talked about last class when we said, you remember we had a decoder, but then we had an extra bit that would shut everything off? So this would be kind of letting that open so that one of the fields could be read from or written to. If we're going to write to any of our 3, our instruction allows for us to refer to 3 of these registers. So for example, if we're going to take 2 numbers that we have stored in a register and add them together and then store the results into a 3rd register, we would fill in all 3 of these fields, the C, the B, and the A. The C is going to be the register where results go. The B and possibly the A, if they're 2 operands, would be where the information is coming from that's needed for the mathematical operation. So yes, and then this encoding will determine whether we're going to store values into our scratch pad. So this is again that bit that allows data to be entered into our scratch pad. Our scratch pad is 16 registers. So C is going to be the register for storing the results. B is going to be a source, and it should have listed A, but A is also a source if it's needed to. And then this is going to be the address we'll go to if we need to go, if our program's next instruction is something other than the instruction right after the current one. If we have to jump somewhere else, we'll do that too. Okay, so, for example, if you had an instruction like in C or Java, if you had an instruction that said something like A plus B equals C, what we're going to have to do on this architecture is we're going to have to somehow, step 1, go out and get the value of A from memory. That'll be one step. Then the second step is we're going to have to get the value of B from memory, also store that in one of our registers. Then the third step would be to perform, and we happen to be able to perform a mathematical operation of adding 2 numbers together. We would add those 2 numbers together, write that result into one of our registers, and then a 4th step would be to take that register and store it back into location C. So on this particular architecture, this would be our instruction format. So we would have to, and this is the way computer programs were written in like the 1950s, the people would have to know the architecture, know what each wire coming out of the processor is, and said, this will be 0, this will be 1, he'd write that. And then a little bit later came up with this idea of an assembler, which would be words that you could write that look a little bit like English, but are describing step by step what's happening. And you could write this, and then a program would generate this. That made life a little bit better. And then later on, higher level languages like C++ and that kind of stuff, you would write this, and the compiler would generate this. And if you wanted to read it, it would generate the comparable assembly language later. Okay, so if we wanted to load the value of A into a particular register, so we said on this architecture, we have 16 registers. So they're numbered 0 through 15. And assembler language usually puts the letter R in front of a register, and then you number it in decimal, because we're human beings, right? We read decimal. So we would number it 0 through 15 in decimal. So we would say, you know, the assembly language might be load memory register A into register 5. Because let's say register 5 happens to be open at the time. So in order for us to do a load from memory, we're going to take data from memory to go through this. So this first mux says I need to pick from here, not here. And the instruction says if we set this bit to a 1, it will accept data from here, not from our registers. So we had to set our mux to 1, meaning I'm going to read from memory. What is our condition? Are we jumping anywhere? Is the next instruction going to be somewhere else? Is it like the end of a for loop and we have to jump back to the beginning, or is our next instruction going to be the very next one? This one, there's no jumping, right? We're just going to load A at the very next line that we're going to run as this one. So, we're running our instruction here. The very next instruction, we're going to take the current instruction, increment it by 1, and let that go through this mux. We're not going to jump anywhere. So I'll do an example later on where I'm going to jump something. So our condition code can be 0, meaning no jumping. So 0, 0 means, putting a 0, 0 here means that this line will be the next line to run. The ALU operation we're going to do is 0, 1, which is 0, 1 means let A pass through untouched. We're just reading from memory. We're not adding anything. We're not flipping bits or anything like that. We're just letting it read through untouched. So that's our ALU operation. We're not going to shift. We're not multiplying by 2. We're not dividing by 2. We're not shifting anything. We're going to open up the MAR to put data into it to get a value to come in. We're doing a read. We're not doing a write. And then we're going to write to, let's say, a memory location. The result is going to go into memory location 5. Okay. The address of A doesn't matter. Oh, and I'm making an assumption here that we already had the address of memory location A was being stored in register 8 and 11. So I'm just making an assumption there. So this is our source, and here's where the result goes. The A register and the address we're jumping to are irrelevant. So I put X's there, meaning they could be 0s or 1s. They won't affect this instruction. So the assembler would probably 0 them out. 0s look nicer than 1s. So, okay. So then we have the next instruction where we're going to also load the value of, let's say, memory location B into, say, register 9. So we're loading the results go into register 9. I'm saying my memory location for, my memory address for B is in register 12. And register A and the address we're jumping to again are irrelevant, so they'll probably be all 0s. Now we're going to hit the next step, where we're going to take the contents of register 5 and register 9 and add them together and put the results in register B. So what we're basically doing now is we have the value of A and B in here. We're going to feed them into these 2 inputs. We're going to set this mux to 0, meaning I want this to come into A, not data from memory. Those two inputs will come into the ALU. We'll set the ALU operation feeding into here will be the operation to add the two numbers together. The result will flow out of that ripple adder thing we did where we have the carry bits. We're not going to shift anything. And then the result will be able to go back into another memory location, whichever we put in C is the location goes to. A and B is where it's the two inputs are coming from. And once again, there's no jumping. We're not going to another address. So the instruction would be, we would have a 0 here, meaning I want to take the A input comes from our 16 registers, not from memory. No jumping. We're performing operation 0, 0, which is addition, right? We said that 0, 0 is take the A input, the B input, and add them together. There's no shifting. We're not multiplying any results. We're not reading and writing from memory. So we don't set the MER and the MDR. We're not doing any reading and writing, so we can shut off all reading and writing to main memory. The encoding is open because we're writing to result to one of our scratch pads. We're writing the results to register 3, and the inputs came from register 9 and register 5. And these bits don't matter because we're not jumping anymore. Then we eventually have to store our value from register 3 back into memory location C. There's no input coming into the ALU, so this bit really wouldn't matter. That could be set to 0. I could have put an X there, meaning it doesn't matter what it's set to. The input doesn't matter at this point. And so the condition is, once again, no jumping. We're letting the value pass through. There's no shifting. Oh, sorry, no, this would have to be a 1. This would have to be a 1 because we're taking the value from register 3. The way this architecture is laid out, we're taking the value from register 3. We can't write directly to memory. We have to let it actually pass through here. So this must have to be set to 0 to let this go through. We're doing operation number 2, letting the value run through without any math done, with no shifting, and then the result would get put into the NVR and sent out to memory. Okay. So on the last step, we are writing to the MER. We are giving a memory location in the MER to store the value into. We're not doing a read, but we're turning write on, which allows one of the memory locations to accept data that we're writing to. And we're taking the value from register 3. And in this instruction format, we always had to take, when we let data go through using a source of register 3, even though we let it pass through, we always had to give a location where we're storing the results to. I even could have left this as 3. I could just take the value of 3 and write it back to 3, and in the process have it written out to memory. And then again, operand A and the jumping location are irrelevant in this instruction. So then, just to give an example of how this processor can handle jumping, suppose you had a piece of code that said, if C is greater than or equal to 0, do this, otherwise do that, right? You've had code that does something like that. So what we would have to do is we would have to take the value of C and perform some kind of mathematical operation on it so that the bits, we have to somehow run it through the ALU in such a way that the N bit and the Z bit get set. So what is the N bit again? The N bit says the result of the ALU operation, is it negative or not? And that's really easy to do because when you represent numbers in binary, the highest order bit, if it's turned on, the number's negative, and if it's off, the number's positive. So to answer, so this wire is really easy. It's the highest order bit. It's just a copy of the output of the highest order bit. So if the highest order bit is on, the value of the result of the ALU was negative. Now, we need a bit that says, is the result of the ALU equal to 0? So if I gave you a binary number, and I said, how can you tell me if it's negative, how can you tell me if the value is 0 or not? Could you wire something together that answers yes or no? It's 0 or it's not 0. So the thing is, if it was an integer, if all the bits were 0, it would be 0, right? And if any bit was a 1, then it's not 0, right? So if you took all the bits and ran them into a big AND gate, no wait, if you took all the bits and ran them into a big OR gate, and the result was 1, what does that mean?
It was 1.
It's,
No.
well, it's not 0.
Not 0.
Not 0. And if you ran all the bits together into a big OR gate, and it came out 0, that means it was 0. So if we need a wire that says turn on if the value is 0, otherwise turn off, that would be pretty easy to do. We take all the bits of the register, run them into a big OR gate, take that output and run it through a NOT gate. So if all the inputs are 0, then the output of the big OR gate would be 0. And then the NOT of that would be 1. And if any of the bits were on, the output of the OR gate would be 1, and then we'd flip it to 0, right? So, yeah, so to build this Z wire is pretty easy. Just run all the bits into an OR gate and take the result and run it through a NOT gate and have the result come out of here. So, by having a number go through the ALU, perform a computation, it's very easy for us to have the ALU also set an N and a Z bit. Is the result negative? Yes or no? Is the result 0? Yes or no? That's an easy thing to create a wire for. And how does that come in handy for us? Well, it comes in handy for us. We can jump when a result, we can set the condition to say don't jump. We can set the condition to say only jump if the result was negative, only jump if the result was 0, and always jump. There's 4 different ways we can set the jump. So, if we have an instruction like this, if C is greater than or equal to 0, what could we do? Well, we could load C into the ALU, and if it was negative, if the value of C was negative, then this statement is false, right? So I'm saying if it's greater than or equal to 0. Now I picked the clause that made that bit work perfect, right? I said greater than or equal to 0. What if this is greater than or equal to 6? That would be a little bit different. But I can write assembly language code that will test for this condition, and if the condition fails, I'm going to jump to some label. So what I'll do is I will say, load the value of C into a register, and that'll set the 0 bit and the negative bit. And then I'll ask myself, I'll say jump if it's negative to that side of the if statement. Instead of having what's in here be the next instruction running, I'm going to jump to here and let that run. Now suppose, suppose this if statement was if C is greater than B. Would we be able to write code over here? So, you know, maybe later on we could talk about more assembly language if it interests us. But could we do something like that? If C is greater than B, is there a way we can check is C greater than B? Because our architecture only seems to handle, two cases. It can check if a number is negative, and it can check if a number is 0. So if we wanted to do if C is greater than B, what we can do is we can subtract B from C. Well, if it said if C is greater than or equal to B, we can subtract B from C and then check if the result is negative or not, right? And how can, on this architecture, how can we subtract? All we know how to do is add. We can add, we can let the number pass through untouched, or we can take the complement of the number. When we take the complement of a number, we calculate its negative value. So we can actually, on this architecture, we can do an if C is greater than or equal to B statement. We would take B, we would load the value of B into one of our registers. We would then take its complement, which is now negative B. We would then take C plus negative B, which is the same as C minus B, and then check, is that result negative? And if that result is negative, then we would jump, otherwise we wouldn't jump. So even though this is a little silly architecture, it can do some basic mathematical stuff. We can do subtraction, it just takes a couple of steps. It would be nice if we built a subtractor in here, take two inputs and let one subtract from the other. But we can do subtraction on this ALU by taking one number, calculating its negative value, and then adding that to the other number. It just takes more steps because it's a simple architecture.